All right, so today we're going to be talking about the math skill centered around water potential and solute potential. Before we get into that, there's a few things that we're going to want to make sure that we understand before we start this lesson. If you don't understand these concepts or these vocab words, it's going to be important that you go watch my other video on tonicity. So this concept, water potential, is going to build on these vocab words. So we have isotonic, hypotonic, and hypertonic. And first, to break down these, we'll want to break down the root word. So we'll talk a little bit now, but again, go watch my other video for more details. So hypo actually means low. Think about like someone who's hypothermic. They have a low body temperature. And tonic means solute. And that's something that's dissolved in the water itself. We also have hypertonic. So hyper, think about someone, this means high. Think about someone who is hyper. Right, they have lots of energy or high energy. And then tonic, again, is talking about solute. Okay, so let's talk about hypotonic. So I'm going to use a different color here. Let's see if we can get one. We'll use red. So this is a hypotonic solution. So that means the area surrounding the cell, the solution, doesn't have that much salt, it has low salt. But that means that inside the cell then has relatively more salt on the inside. And so what's the result going to be? It means that water is going to flow into the cell. So we can see that here. That's why water will flow in. In an animal cell, that's going to lead to the cell eventually bursting. So you can see it's kind of like exploding at the seams here. And so that would be really bad for an animal cell. In a hypertonic solution, however, hypertonic, right? That means lots. So here there's actually lots of solute on the outside of the cell. And that means there's very few solute molecules on the inside. So what's going to happen? Water is going to flow out of the cell, and the cell is going to shrink or shrivel. Isotonic is a little different. Isotonic means there's an equal amount of solute on the inside and the outside. So water is going to flow in and it's going to flow out equally. So, or be in equilibrium. So the cell is happy there. Now, each of these situations is slightly different when we're talking about plant cells. So for more information on that, again, go watch my video on tonicity. Okay, so what are you going to have to do to be able to calculate water potential and determine what it means? So first off, let's go over the definition. So water potential is how likely water will move in or out of a cell. So this is going to build on our understanding of osmosis and tonicity, as I mentioned before. So water potential is given the Greek letter psi. Think about like Poseidon has a trident, right? That's where psi comes from. And so we're talking about water. And it's, again, the measurement of how likely it is that water will move in or out of a solution. And we'll talk about why pure water is assigned a water potential of 0. So we'll talk about that when we get more into the equations. We're just going to understand the conceptual part of it first. The big piece for our conceptual understanding of this is going to be that the more negative the water potential, the more likely that water will move to that area. So let's see an example here. Well, first, I guess maybe here's a one way to picture this, right? So a big water potential, the water will move towards the smaller water potential. Or in this case, right, if we use that definition, this is a more negative water potential and this is a more positive water potential. Water will move towards the more negative water potential. So I'm going to challenge you guys right now to pause the video and try to determine which way water will flow. Okay, if you paused it, most of us probably said that water is going to flow out of the cell, right? Because from our last concept, we said that water will flow from a high water potential to a low water potential, right? And so 2.5 is a bigger number and zero point 0.5 is a smaller number, so water should be flowing out of the cell. However, we have to think about this in a slightly different way. So I'm going to use a number line to help us understand this. So we're probably familiar from number lines with number lines from our math classes. 0 is going to be in the center. These are going to be positive numbers over here. These are going to be negative numbers on my number line. And so just a thought question here. So which number is bigger, 0.5 or 2.5? Which number is bigger? Okay, obviously 2.5 is a bigger number than 0.5. Now, what if we did that on the negative side of our number line? Okay. So relatively, which number is bigger now, negative 2.5 or negative 0.5? Well, this is a slightly different question because in this case, because we're talking about negative numbers, negative 0.5 is actually a more positive number. It's a bigger number than negative 2.5. Negative 2.5 is actually more negative. So in this case, it's counterintuitive, but again, using the number line idea, we can think about this. So this number is actually our more negative water potential. So just as we predict, water will move from a high to a low water potential, and negative zero point 0.5 is actually a higher water potential. So water is going to move into our cell. If that wasn't quite clear, you can go ahead and read this description, pause the video for a second. So if you pause the video, that's the basic conceptual understanding. And where we'll get to eventually is how do you actually calculate these numbers like negative 2.5 and negative zero point 0.5? Right now, we're just trying to understand, okay, given those numbers, how do I figure out where water is going to move? Now, what's the significance of this for life on our planet? Well, we can connect this to some ideas that we learned in Unit 1. So in Unit 1, you learned about things like cohesion and hydrogen bonding. You learned about adhesion as well, how water sticks to itself and then sticks to other substances. But how can this help us build on our understanding of why does water, so I'm going to use a new color, we'll use blue. So here's all this water down here by the roots of this tree. How does that water actually make its way up the tree to the leaves and then eventually out into the air? How does that happen? Well, we can use water potential to understand that. And if we measured the water potential, there's actually, we can use, so here's negative zero point 0.8, negative zero point 0.3, negative 1, negative 100 in the outside air. And so using our understanding of water potential, we know water is going to flow from where there is a large water potential towards a low water potential. So negative 100 in the outside air is actually a really low water potential. And so the water potential down here at negative zero point 0.3 is going to be pulled. This water will be pulled to an area of lower and lower water potential until eventually it leaves out the leaves, no pun intended. Okay, hopefully that helped with the conceptual understanding of water potential, and we'll see you in the next video.